This might be the most underappreciated optimization in the entire LLM ecosystem. Like the architectures we have been discussing in our previous videos, this doesn't changes anything in the entire model itself. Instead, it fixes the massive flaw in how we schedule requests onto the GPU. Shifting from rigid queues to fluid scheduling, serving throughput instantly jumped 10 to 23 times over. Hello everyone, welcome back to my channel. Today we are breaking down the mechanics behind this massive leap. That is, static batching versus continuous batching. So let's first understand why batching matters. Modern GPUs are massively parallel. An H100 has 16,896 CUDA cores. A single request doesn't saturate them. If you serve requests one at a time, you are wasting 90% of your GPU. Batching solves this by processing multiple requests simultaneously. In a batch, the matrix multiplication for all requests can be computed together. A batch of 8 is barely expensive than a batch of 1. So why isn't this solved? Because LLM generation is variable length and sequential. So let's now understand the first thing or the first type of batching, that is static batching. So this is the naive approach what most systems did before 2022. That is the static batching. Here the process is like this. You collect n request, pad all inputs to match the length of the longest one in the batch. Then you run until every sequence in the batch finishes. Only then return results and pull the next batch. The third step is where the problem is, or it falls apart. The first problem in the third step is like the padding problem. That is, if request A finishes in 20 tokens, but request B needs 200 tokens, then request A's slot in the batch sits idle for the 180 tokens or remaining 180 steps. The GPU is still doing work, just that is meaningless work for padding tokens that produces nothing useful. The second problem in that step is the batching delay problem. New request can't join until entire batch is done. If 7 out of 8 requests finishes quickly but one runs longer, every request is stuck until waiting in a queue, even though there is idle capacity sitting right there. Real deployment measured this. Typically, static batching achieved only 10 to 30% GPU utilization. The other 70 to 90 was wasted on padding and on waiting. This was the industry standard until 2022. To fix this, in 2022, a paper called Orca introduced continuous batching, also known as iteration level scheduling. It changes exactly one thing, but that one thing matters enormously. Instead of scheduling at request level, schedule or at the token generation step level. Here's how it works. At every generation step, the scheduler asks two questions. First, did any sequence in the current batch just finish? Second, is there a new request waiting? If both are true, the new request slots in immediately. No waiting for the rest of the batch. This means that the batch is always full, no waiting, no padding waste at the request level. Let's walk through this animation. So in the step 1, slot holds request A, B, C, D all generating. Step 2, as B finishes, it immediately replaced by E. Slots now hold A, E, C and D. And step 3, if A finishes, F takes its place. Now the slots hold F, E, C and D. No slot ever sits idle between requests. The batch is always full, as I said. Why this is harder than it sounds? Every sequence in the batch is now at different position in its own generation. And one request might be in its first token and another on its 50th token. That means each sequence needs its own KV cache at its own length managed independently. This is exactly why paged attention matters here. It lets the KV cache live in non-contiguous memory blocks. So the scheduler can swap sequences in and out of the batch without needing one giant contiguous allocation for every slot. And but here also we have one subtlety, like as we discussed in LLM generation has two phase, prefill and decode. So the prefill is processing the input prompt, which is parallelizable and compute bound, and decode is like generating tokens one by one, that is sequential and memory bandwidth bound. These have different computational profiles. Native continuous batching can cause prefill decode interferences, like a new request prefill slowing down ongoing decodes. Now, to solve this problem, modern serving systems go well beyond basic continuous batching and implement four techniques that are worth noting. Like the first one is chunked prefill. So instead of processing a long prompt in a one giant burst, it splits it into chunks and interleave those chunks without ongoing decode steps. No single long prompt can monopolize the GPU and cause a latency spike for everyone else. And it is used in VLLM, SGLang, and TensorRT LLMs these days. The second one is disaggregated prefill and decode. This run prefill and decode on physically separate GPU cluster, one tuned for raw compute throughput and the other tuned for memory bandwidth. Request gets routed to whichever cluster matches the phase they are in. And this is how the largest production deployment squeezes maximum utilization out of both workload types. The third one is priority scheduling. Not all results deserve equal treatment. An interactive chatbot needs low latency. A background batch can tolerate waiting if it gets higher throughput in exchange. So the scheduler balances both inside the same system. The fourth technique is KV cache prefetching. While one request is still decoding, the system can prefetch the KV cache for the next request in line, hiding memory latency behind compute that's already happening. So none of these change the model. They are all decision about when and where work happens. So if we look at, or let's put the real number on this. The original Orca measured up to 36.9 times higher throughput with continuous batching versus static batching on GPT in certain configurations. Real world benchmarks from VLLM tells a similar story on 70 billion model running on a A100 GPU. So in the static batching had roughly around 300 tokens per second, and in continuous batching it was roughly around 3000 to 5000 tokens per second. That's a 10 to 15 times improvement in practice, slightly more conservative than what the paper suggested, but still enormous. And translate that into cost. If you were paying $100 an hour to serve a model with static batching, continuous batching can deliver the same throughput for $7 to $10 an hour. This is the single biggest reason VLLM, which pioneered paged attention with continuous batching, became the dominant LLM serving framework almost overnight. So to conclude or summarize static batching versus continuous batching, one scheduling change can bring the throughput to 10 times better. The lesson isn't just technical, it's that sometimes the biggest win in engineering aren't about the algorithm or the model. They are about how you are using the hardware you already have. If you followed this whole series, you now have the understanding of four pillars of modern LLM inference stack, like the attention mechanism that determine how the model processes token. Quantization determines how much memory it needs. Speculative decoding determines how fast it generates. And the batching that we discussed today determines how efficiently you can serve multiple users. These four pillars are what major LLM inference framework like VLLM, SGLang, TensorRT LLM or Llama.cpp is built on. So in the next upcoming videos, we will be seeing more about the production or scaling the LLMs or these LLM inference in the production setups. Thanks for watching. See you next time.